Now, we weren't able to complete all the problems I'd hoped to finish in class, so I've made this video to set you up for the practice questions. Now, this question on page 185 of the text has a tractor being pushed by a plane, and I've already sketched these to speed up the process. So the question talks of the tractor exerting a force backward on the runway, but of course Newton's third law says that the runway exerts the same force in the opposite direction on the tractor. And of course this force acts on the total mass of the tractor and the plane combined. And before we start, we'll establish our directions, positive and negative. Well, let's set up our free body diagram. So we have gravity acting on the system, and the runway provides a normal force. Then the force of the runway on the tractor pushes the system forward, while the forces resisting the motion, that we'll refer to as friction, act backwards. And this takes us to our calculation of the net force in the x direction, which is the sum of all the forces in the x direction. Now the net force causes the masses of the tractor and the plane to accelerate, while the forces acting on the system are the force of the runway on the tractor and the friction opposing the motion. So let's isolate for the mass of the plane. First, we'll divide both sides of the equation by the acceleration. Then we'll subtract the known mass of the tractor from both sides. Now we plug in our values, remembering that the friction will have a negative value, to find the mass of the plane, which turns out to be 9.89 times 10 to the power of 4 kilograms. And finally, we end our solution with our therefore statement, since we were asked the question in English. Now part B of the question has us determine the force of the tractor on the plane. So we've isolated the plane here, and the forces informing the motion of the plane will be the force of the tractor on the plane, as well as the portion of the friction acting on the plane alone. And our free body diagram will consist of the plane's weight, the normal force, the force of the tractor on the plane, and the friction. And this takes us to our second law calculation, where the net force in the x direction is the sum of those forces. And this net force causes the plane to accelerate due to the force of the tractor on the plane and the friction. So we'll isolate the tractor's force by subtracting the friction from both sides. And we'll substitute our values, again with a negative friction, to find the tractor exerts a force of 1.7 times 10 to the power of 4 newtons on the plane. And we won't forget our final statement. Okay, so let's look at one more. Here we have a basketball player jumping for a ball. But for this one, we'll have to separate our analysis into two parts. First as he's pushing on the ground, then when he's in the air, in free fall. We have to do this since the physics at work change when he leaves the floor. So in part A, his initial velocity is 0 and he undergoes an acceleration that we don't know yet over a distance of 0.3 meters. Of course, his final velocity in this part is the initial velocity when he's in free fall. Here, of course, his acceleration is 9.8 meters per second squared down, while he reaches a height of 0.9 meters before his velocity is 0 as he changes directions to fall back to the floor. Okay, so we set our directions positive and negative, and we'll use a big 5 equation to determine this initial velocity in free fall. Now v2 simplifies as it's 0, and we'll subtract that acceleration displacement product from both sides, and then take the square root of both sides to find v1. And don't worry about that negative sign under the square root. Our negative acceleration due to gravity fixes that. Now we can substitute our known values, and we find that he leaves the floor with a velocity of 4.2 meters per second upward. Okay. So now we're ready to find his acceleration while he's jumping before he's in free fall by using the same big 5 equation with our values before he jumps. This time v1 simplifies, so we just have to divide both sides by 2 delta y, and we'll substitute our known values into the variables again and find that he accelerates upward at a rate of 29.4 meters per second squared. So now we'll set up our free body diagram to determine the force he pushes with to make the jump. As usual, there's his weight, his force of gravity. And the normal force must be larger than this in order for him to accelerate upward during his jump. Then we use the third law to determine the opposing force he exerts on the floor. And this takes us to our second law calculation, where our net force is the vector sum of the forces in our free body diagram. With the net force causing him to accelerate, and the forces being his weight, the product of his mass and the acceleration due to gravity, and the normal force, we can isolate the normal force by subtracting his weight from both sides and factoring his mass to simplify the expression. Substituting our known values, we find that the normal force is 4,312 newtons. This means he exerts a downward force of the same magnitude on the floor to make the jump. And finally, here are some practice questions that should help you develop your skills at analyzing the relationships between force and motion using Newton's laws.